Hello, guys. This is the 21st lecture of the Physics 140 of the semester. And today we are going to continue looking at the quantum mechanics of three-dimensional systems. And let me get started here. Sorry about this. Okay, so there is some pointers here. There is some changes in the let me see if I can use the arrow, which should be bigger. No, I don't like that. There's some changes in the I cannot do that. Okay, perfect. Now the size is a bit larger. So we were looking at the effect of the Schrödinger equation in the description of the, I would say, more basic example of where quantum mechanics should work, which is atoms, because in atoms, the electrons are confined in a very small volume, and when that happens, when the volume is of the size of the angstroms or whatnot, you can see very strong quantum effects. One of the most important quantum effects that one could see there under these dimensions is the quantization of energy. Okay, so we find that in the case of hydrogen, we have energy levels, and we can somehow have the feeling of the other atoms that could also be described in similar terms. And that's what we were discussing in last classes. In particular, the differential equation that describes the potential for the radius is it is modified in the case of the different atoms simply by modifying by a different radial potential than the one provided by the electron-proton interaction, which is simply the Coulomb interaction for the potential, which is E squared over 4 pi epsilon 0 r. Okay, so essentially we see that there is this thing that the actual charge that the electrons see is not exactly the same charge that the nucleus have, because there is a screening effect of the other electrons participating in the in the inner, not participating inside the inner shells or the core of the multi-electron atoms. So the solution, nonetheless, for the angular differential equation is exactly the same as for the helium, for the hydrogen atom. So we get quantization of angular momentum, because quantization of angular momentum is not related to confinement. It's something that occurs in free space, and it happens here. So the angular momentum is quantized also for all of these electrons. And they have sort of the same rule as before, meaning the value of n somehow limits the value of L. So this is what happens in the actual electronic orbits in the different atoms, and so we still have the rule that L is equal to n minus 1, and obviously the quantization for the angular momentum has nothing to do with the radial solution. So we still obtain that for each value of L, we have 2L plus 1 possible states for the angular momentum, and if we add that to the electronic spin, we have twice the number of states for each level, okay? Not the number of the states are the same. We have two, we can put in each state 2 electrons, okay? That's a better way of saying it. So this notation was developed. The L equals 0 state is called an S state, and the one in front corresponds to the N value. So the 1S state in the case of hydrogen will be the lowest available state, and that is the basic state that one ground state hydrogen atom can have, meaning the electron goes into this lowest energy state, and in this case is minus 13.6 electron volts, okay? And it's a 1s state, and then when I use helium, I increase the, there's 2 protons in helium instead of 1 in the case of hydrogen, and so the cloud of electrons is almost like hydrogen, but with a higher charge. So and that what that does that is just bring the electrons closer together. So the electrons in helium are more tightly bound than in the case of hydrogen. And again, the first state is a 1s state, and a 1s state can hold 2 electrons, 1 for each value of the spin. So I could have a spin up and spin down, and I can start filling this table all along in the same way. And we have developed this notation here. No, we haven't. Somebody developed this notation here that the number in front, the 1 means n equal 1, the s means L equals 0 state. The 2 here means this second level is n equal to 2, and the s level here is filled with 2 electrons as the one in the first one, in the 1s, and in the then, since the value of L can go up to n minus 1, so it can go up to L equals 1 in the second level, in the second shell, and here we have, and this particular atom is fluorine, and it has 5 electrons in the p states. Okay, so I have 5 p electrons. I have 3 values of m equal minus 1, 0, and 1. And for each one of this value, I can put 1 electron up and down until 1 is completely, it's up or down. And that's the configuration of the last occupied electron, okay? In the case of fluorine. We can only put 1 electron, I'm sorry, we can only put 2 electrons because the spins have it gives 2 possibilities of quantum numbers, spin up and spin down. So for each particular level of solution of the Schrödinger equation, I can put 2 electrons in each one of those levels, okay? So that's why finally the p states, which are only 3 possible values of m, minus 1, 0, and 1, can hold 6 electrons, because you have to, for m equal 1, I can put 2 electrons, 1 will spin up, 1 will spin down, with 0, 1 will spin up, 1 will spin down, and so on, okay? So essentially the field layer will be 6. In the case of the d electron, the field layer will be 10. In the case of the f electron, the field layer will be 14. And that's about it, okay? And then when we run out of elements, essentially, okay? So these are a few of the elements, and these are the interesting electronic configurations, and we have this sequence of numbers. And in the previous case, in the case of the hydrogen atom, which is something that we solved and studied in more detail, we found out that the energy wasn't independent of the value of L and ML, okay? So the energy didn't depend on those values, despite the fact that they were included in the equation. So the energy only depended was dependent on the value of n, the main quantum number that it comes from the solution of the radial equation. Okay, and in this particular case that we're looking at atoms with multiple electrons, or with many electrons, the situation is a bit different because the function that you put in the radial equation is not 1 over r, is some function, it's a radial function, but it's not 1 over r. So this solution retains the radial symmetry, but it does not, you know, there's some problems with the, not a problem, there's a difference between the hydrogen atom and this main atom now that the energy can depend on the value of L. As we can see here, there are some singularities. For example, the first singularity that we see is that essentially the 4s electron, where is the 4s electron? Here it is, the 4s electron is here, see, after the 3p electron comes the 4s electron in terms of the energy levels of the solution. If this was if this atom were a hydrogen atom, the next level should be the 3d electron that it should start piling up, because that should be there's no energy dependence on the L value, but here there is an energy dependence. And actually this value here, the fact that it has to do with the screening of the inner layer electrons that are doing of the different orbitals in this material. So this is the reason why we see this slight change in order, and so there's a nice way to actually represent this, and I'm sure you have seen this before, but now we are justifying it from the point of view of quantum mechanics, and these SPD values have a meaning in terms of the quantum numbers that the electrons have inside the electronic configuration of the atom. Okay. So let me go to the next slide. So we essentially can produce the periodic table as such, and in principle this should be a line of elements, and it should not be periodic in any way. But the fact that actually the periodic table, as proposed by Mendeleev, was found this periodicity before anybody knew about quantum mechanics. Okay, so the chemistry knew enough about the atoms to actually say that you know, the carbon and silicium should be in the same column. Actually, this, if you look at each one of these columns here, what changes is the value of n, but the value of s and the number and the exponent of s, the exponent of s, remember, it's the number of electrons in the, or the, in this case it's not s, it's p, you know, in this column. The configuration of this element is 2e squared, 2p squared. All the atoms all the elements in this column have an electronic configuration that is 2p squared for the valence electrons, for the you know, the highest occupied electrons. So that give them, you know, some sort of a common feature. The angular aspect, the number of n is changing because here is 2, 3, 4, 5, and so on. Okay. But the number of s electron in each one of the columns is the same. The number of d electrons here is the same, and that is why chromium, molybdenum, and tungsten, you know, behave chemically very similar. And the same thing could be said about oxygen, sulfur, and selenium. You know, and the chemistry of them depends mostly on what the outside electrons are doing, and this is consistent with the model that we have seen before. So there's a nice confirmation of these periodic properties of the elements in this table. Okay, so I would like to get into more details about the an example that has to do with screening, and this is the screening in the case of sodium that has Z equals 11, and I have here sort of a graphical picture of how this could look like. So I have here the energy levels, and here, you know, I'm just putting in the number of electrons that go into each one of the configuration. If this guy is an S state, it's a 1s state, it can only hold 2 electrons. We know that already. So these are the dark spheres here represent the electron. In the 2s states, I have the same thing. This would spin up and this would spin down. So these are all occupied state in sodium. When we get to the p state is completely filled. The p band is completely filled. It means that or the p level is completely filled. And here we have have 6 electrons here. And if we add up all these electrons, this is the configuration of 10 electrons, and 10 electrons, if we look at, correspond to neon. So that's the configuration of neon, which is a very stable atom actually, because it has a closed shell of electron. It's almost a ball, like with no holes on it. Okay, so in terms of reacting with other elements, they do not. You know, they very much keep the electrons for themselves. It's a very stable configuration. But if we add one more proton to neon, we form sodium. Well, if we add one proton, we have to add one electron too. So we have, you know, the proton and the electron goes on, and the next electron, in the case of this case, will be established in the 3s position. Okay. When we think that this is almost a lone electron here that gives most of the properties to sodium, that's a very nice confirmation. But then when we start thinking, where should this 3s electron be? What should be the energy? We would like to calculate it sort of, not in detail by solving the equation, but roughly speaking, okay? What would be the energy of that state? Well, you know, if we were thinking on screening, you could say, well, these 10 electrons here, we actually are fairly close to the center of the atom, and if the geometry is such that this works out, one in principle could say, well, you know, those 10 electrons can actually screen the positive charge of the 11 protons in the nuclei, and then the most external electron, what it should see, if the screening is perfect, it should see sort of effectively like a hydrogen atom, because it will be something that has a spherical symmetry with a net charge equal to 1 electron. Okay, if that's the case, then the energy of the 3s state should be 13.6 divided by 9, which is equal to minus 1.511 electrons. But if I look here, these are the experimental energies. This gives me a value which is minus 5.138. What does that mean? Well, it means that my model is not correct. There's something wrong, and definitely there's something wrong with it, because it's a good value. So what I'm saying, the incorrect part of my model is assuming that the screening is perfect. The screening is not perfect. Why? Because the 3s electron actually has a shape. If you remember in the previous lectures, the 3s electrons penetrate deeply into the core of the other field electron, very close to the nuclei. So if that's the case, it will be seeing a lot of the 11 electrons most of the time. So the screening won't be perfect. Okay. So essentially, there is a value which is, it cannot be Z equal 11, which will mean that none of these electrons are there, and cannot be Z equal to 1, because we see that Z equal to 1 doesn't fit with the experimental prediction. So the effective charge seen by the 3s electron in the case of sodium is somewhere in between, okay? So this is a good model to start thinking of it. But in the case of sodium also, there are other excited states. There are unoccupied or empty states above that could be sort of populated by electrons or populated by electrons from this material, meaning I could excite states here or there, and they will make a transition afterwards. And we saw some of those transitions before. So between the 3s and the 3p, for example, that gives the color to the sodium light. But where are those states located? Well, the 3p state is at minus 3.035, okay? So that's also a problem because, not a problem, it is showing here that the p states are also going inside the region of the occupied cloud of electrons in a way that an electron populating the 3p orbital will actually see an effective charge that is different from one electron. It could be 2 and a fraction of it, okay? But look what happens with the 3D electrons. The 3D the 3D orbitals are orbitals that really have most of the cloud outside the cloud of the other electrons. So it's almost like the 10 electrons in the inside of the nucleus are actually screening perfectly the 11 protons in the nuclei. And if that's the case, then the model with Z equal to 1 should work very well. And look what happens. This is the actual energy of the 3D electrons. So it should be minus 13.6 divided by 9. It should give here 1.511, and it gives 1.521. Perfect. You know, this is a good thing. Okay. But this is the 3D electrons. But look what happened with the 4s electron. The 4s electron has a wave function. Again, the s electron has these nodes that go very close to the center of the nucleus, and they have a presence very close to where the nucleus of the atom is, and hence it has a higher binding energy or a lower stable energy with respect to vacuum. Okay, so this state is actually lower, even though it is 4, which means that it should be higher in energy than a state with 3, at least in the hydrogen atom. Here we see that we start to see this difference. And this is particularly true in this case. So what I wrote here is not correct, meaning this guy should be down here and this guy is up here according to this measurement here. Okay, so this is the effect of the screening in this material. So as it says here, for states closer to the nucleus, the outer electron penetrates the cloud of the 10 electron, producing an effective charge. So because I could see part of the nucleus going in. Okay, so this is the model, and the way to account for the effective charge is this one over here. And why is this? Because let me remind you that the expression for the 13.6 electron volts, where does it come this 13.6? Is actually from evaluating this term here, okay? And this term here has 2 contributions. And for the e to the 4th here is e squared, that is coming from the charge of the proton, and e squared that's coming from the charge of the electron. And if I increase the charge of the proton, instead of being 1, I increase it to Z or C effective, whatever it is. So essentially, one of these e squared has to be changed by C squared times C squared, because it's the charge of the nucleus square. The charge of the nucleus square is C squared, CE squared. In the case of C equal 1, it gives simply E squared multiplied by the charge of the electron, give E to the 4th, okay? So this is the right expression quantum mechanically for the binding energy of something that's C as CF squared. So you could actually, you know, getting this expression here and tell me what is the effective charge that it's actually the electrons in the n equals 3 states are seeing of the nucleus, because it should be something between 11 and 1. Okay, it cannot be something else. And you tell me, you know, if what value is that? You know, this is not an exam question, but you know, it's worthwhile recognizing, or you know, putting in the calculator and finding out. Okay. This what I'm showing you now. It's the production of X-rays. This we have seen before. What part did we see before? We saw that how do the X-rays are produced? I try to remind you of that. Is you have a filament in one part, and you accelerate the electron from the filament to which is the cathode, to the anode, which is the material that actually stops the electrons. And in the worst case, and what happens when an electric charge is accelerated, it emits energy. Okay, and the maximum amount of energy that the electron can emit would be the total kinetic energy it brings to in the collision with the anode. Okay, so this guy is 35 kilo electron volts, as it says here. So this lambda minimum here, which is the maximum energy of the photons emitted, is directly related to this energy here. Okay, so even if you don't know exactly, you know, if the scale of this graph, if I tell you that this is 35 kilovolts, which means a kinetic energy of 35 kilo electron volts, you should be able to predict exactly with two significant figures what the value of the lambda minimum for that case should be. Okay, but you know, this is what we saw before, and then we have this continuous spectra that has to do with the way, you know, there's more than one way. You lose all the energy at one point, or you accelerate a bit, and with collisions with the electrons, which doesn't produce such a drastic acceleration. It produces a smaller acceleration. It can get into the material, deep into the material. So you have a complete distribution of the way the frequency emitted by the electrons after they collide with the anode material. But again, there are some peculiar things here that we have been ignoring. The elephant in the room is these big peaks that appear here, K alpha and K beta. These are sort of a graphic that somehow explain how the actual experiment works. So those peaks that are called K alpha and K beta are very sharp peaks, and actually they are produced by transitions in the anode material. What really happens is the following. Some of the electrons that come in, one of them loses completely the energy, the other makes this sort of small transition, meaning with the accelerations that are somehow limited, and some of them actually kick the 1s electron of the anode material. If we have the anode material doesn't have the 1s electron at the bottom, what happens, it has an empty state there, and that empty state there is occupied by an electron that comes from the top and decays to that hole there to make it you know, stable again. And for that transition to happen, the electron that makes this optical transition down emits a photon. What is the energy of the photons? The difference in the energy levels. There's no surprising thing here, okay? So we have to find a model to actually describe this. By the beginning of the 20th century, this guy, I don't know, it was Peter Morse mostly, Mr. Mosley decided to actually look at the energy of the K alpha and as a function of Z. And he found out this experimental curve here. He did various points and put the zirconium, copper, cobalt, blah, 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 all these elements here. And he actually found out that energy, the energy of this, or the frequency, which is equal to the energy, or the square root of the frequency, was linear with the z of the element. Okay, the higher the z, the higher the frequency of the element. Right, you know, this was sort of an interesting curiosity for a while. And what we're going to see in the next view graph is a model based on very simple description that takes into account screening to actually understand why this curve has this form. Okay. Today, it's a very useful tool. This Moseley law. It's used in microscopy to actually identify elements in certain regions of, you know how scanning electron microscopy works. There is a beam of electrons that is aimed at a sample, and what one mostly see is the inelastic electron emission from essentially the not only inelastic. No, I'm saying this wrong. Is the is the electrons excited by the main beam that you're seeing? So it's what they are called secondary electrons. If you measure this secondary electron emission as a function of the position of the main beam, which is something that has something like 35 kilo-electron volts, something like this, and you measure the secondary emission and the intensity of the secondary emission, you can get a very nice image of what the surface is, and that's exactly how scanning electron microscopy works. There was one, you can get morphological information very clearly, much better than any optical resolution will make, because actually the electrons have a wavelength that is much shorter than the wavelength of light, so meaning the diffraction effects are minimal, and you get resolution down to the nanometer range with good you know, image resolution. Okay. But there was a problem of identifying the elements on a technical sample that people built. So somebody noticed, well, you know, this mostly law around. Why? And we're using electrons, which is what the guy used. You know, you kick the electron out of the 1s, and if I have 35 kilo-electron ball electrons, I could kick the electron out. So inside the microscope, there should be a lot of X-rays by the emission of the atoms in the sample from the two level, the L shell to the K shell, which is the 1s electron. Okay, and they actually designed something like that, and they put another detector in there to detect X-rays. So actually now you can correlate the emission for a certain position with the intensity of a particular energy in that detector. And actually you can measure the energy in the detector, or essentially the frequency, and that is sort of calibrated, and then you can recognize which are the elements present on each one of the spots. So this technique is actually something very useful technologically, in the sense this is not some Moseley law, who cares, no? It has a lot of implications in actually identifying elements in on microscopic level. Okay, so what is the model for this particular system? Is let me see. Okay, so for this particular system, the model is the following. So this is the starting situation when you just shine the cathode. This is the cathode. This is the place where the electrons are bouncing from. It's accelerated and actually kicked one of the electrons of this material out of the cathode material. And I have the L shell here. This is n equals to 2. And this, what will happen naturally is that this guy will fall down here with maximum probability. The one that is closer to this one will have a maximum superposition to actually decay here. And this transition is an optical transition, and the energy that this electron will lose coming down here will be exactly one electron, will be the difference between this level and this level, will be a very well-defined energy that has nothing to do. So these peaks here stay in this position no matter what. If I change it to 45, the K alpha and K beta will be exactly in the same position for this graph, okay? And does it say this is a molybdenum target? In the molybdenum target, you will have the K alpha and K beta. Why? Why does it not depend on the energy of the incoming electron? Well, because we forgot about the energy of the incoming electron. The incoming electron, the only thing that it did was kicked out this, it must have enough energy to kick out the 1s electron of the molybdenum target, okay? If that happens, this will be free, and this guy will make a transition, and we will forget about the energy of the incoming electron, okay? And this is good, you know. If we do this experiment with different values, what will change will be the cutoff here. If I go to, let's say, 45, I will move the cutoff, you know, this way. If I go to a smaller energy, meaning the cutoff will be here, okay? And these peaks will be lower because if they will, the incoming electron will not have enough the same efficiency to actually remove the electrons from the core in the case of the 1s electron in molybdenum, okay? So this is the model. So this is the starting point. This starting point has this energy. Then this guy here, this electron in this position here, what does it see? All these guys here see that this is far away. So this is actually the L shell, the electrons that are closer to the ion. So a good approximation will be that these guys over here see the charge of the nucleus -1. Why? Because there's one electron always present in the 1s state. We are only kicking one out. The other one is there. So the effective nuclear charge should be C-1. So the energy of the L shell for this excited state, this is an excited state of the atom because, you know, these guys shouldn't be there, it should be here, you know, because the energy should be lower. And then there's a lot of cascades here that go on afterwards to actually refill the states here. Actually, the material is connected to ground, so it doesn't lose charge, okay? At the end, you know, there are electrons around that will fill these states easily, okay? So but we are seeing the impact of the emission of radiation, and that's exactly what happens. Then the energy will be, if you remember from the last view graph here, oops, this one over here, the Z effective here now is Z-1. I have the 13.6 electron volts, and I'm in the N equal 2 level. That's the L shell, okay? In this case, it's the L shell, the N equals 2 level here. So, and this is the 1s, and this electron here, the energy of this electron is well represented by simply the screening of the nuclear charge by one electron. So that's C-1. That is the effective charge the electrons in these levels are seeing, and this is the initial energy for a transition. This is the initial energy, and then what happens is the electron comes down from here to populate this state. To what state? To this state. When it comes down here, this electron is still screening this other electron that is coming from the higher energy level. So the energy level of the final state is minus 13.6, there's a point missing there, divided by 1, this should be a 1 there, times Z-1. Z will be the charge of the nuclear, you know, the nuclear charge. And the -1 there is why? Because this guy is always screening in both situations, okay? So this is my model. You can argue about it, okay? You can say, oh no, the screening is not perfect, blah, 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 blah. Well, but the only way to actually recognize if the argument is right is to, if it is possible, it's possible. And if it is possible, you can say this is a good model if it actually describes nature as it should. And in this case, it does. It produces that the delta energy of between E final minus E initial is the difference between these two things. This is the, I mean, the final energy plus the energy of the photon should be equal to this, okay? So what is the energy of the photon? The energy of the photon I call delta E. Delta E is equal, and then to this difference is 10.2 electron volt times C minus 1 squared. So I square root this guy, take the square root of this, take the square root of that, and the square root of the energy is the square root of the frequency. So I have the same expression like this. I have an expression that the square root of the frequency is linear with respect to Z. And you know, intercept and an intercept C equal 1. This line is perfect. You know, it should go to Z equal 1, which is exactly that. Meaning the intersect of the line, when I take out the square root, is that. Okay, so this is the theory here using the screening that actually produce the same qualitative model. And it would be nice if you guys could check if this theoretical line, not theoretical, it's experimental line drawn here over the actual values has a slope that is coincident with the slope predicted by this number here. Okay, this is what it's the interesting part. I don't know if this value is right actually. Yeah, I guess it is, because here I have hertz and here I should have square root of hertz. Yeah, square root of hertz, perfect. And you can see this is 10 to the minus 8 and this is 10 to the 15. So the numbers -8, 10 to the minus 8. No, this cannot be right. The frequency should be 10 to the 8th. 10 to the minus 8 makes no difference. Hertz. Yeah. 10 to the minus 8 is something that never happened. Okay. Okay, well, you know, check this number out actually, and see if it compares well with this expression that I have here. The fact that it's square root of 2, it gives that this number should be close to 10 to the 15. Okay. Okay, guys. In this transparency now, we see this line diagram here, schematic line diagram, which shows where are the different lines associated with different materials of the anode, meaning the material on which the colliding electrons hit. Okay, this is tungsten, this is molybdenum, and this is copper. But you can imagine that the Z number of this thing goes that way. So Z is higher this way than this way. Why is this? Because the larger the wavelength, the smaller the frequency. Okay, so in this particular graph here, whoops, where's the graph here? So if we are here, this is a low number of Z, and these guys, molybdenum and tungsten are up here. So essentially, we are looking at K alpha, but each one of these lines, there's more than one line. That's the point. Okay, so the diagram, the intensity diagram, you know, similar as before. We have the lambda, minimum lambda, that has to do with the total energy of the incoming electrons as before, and you have peak that is the gamma peak, the beta peak, and the alpha peak. The alpha peak is the one that we have been describing, but the other ones, I'm sorry, the alpha peak is this peak here. This line things is color coded. This is the Gale shell, L, M, and N, and this guy here is the alpha peak, which corresponds to this guy over here, and we have all these other peaks that also appear that have larger energies, less smaller wavelength. Okay, this is the lambda and so the beta and the gamma peak. Okay, beta and gamma. Okay, so that is what we are seeing here, and the good thing is that this experimental result can be easily explained by the simple model of the screening on the nucleus. We need to put in some quantum mechanics. We need to understand the 13.6, the effective charge, the removing of things, and even if we cannot obtain the actual orbital wave function, you know, we can take some elements out and use quantum mechanics to explain the real world, and this is something that an engineer should be able to do. Okay, so now I'm going to change subject a bit and to a more I would like to say more on the borderline of quantum mechanics, and I would like to talk about entangled state, because this thing has sort of a strange implication in terms of quantum mechanics. Okay, so I'm going to follow the text that I have here. So let's assume we have two particles. We have an S missing here. We have two particles wave function that is a solution to a Hamiltonian. If it is a solution to a Hamiltonian, it means that I could write it as a wave function of space times e to the minus I et over h bar, which is exactly this term over here. So I solve this. So this is each one of these r here's are the position of one electron or one particle in a certain part of the system, and this is the position of a different particle. It's a two-particle wave function. And when I solve the Hamiltonian, it behaves like this, and so this is the energy of the Hamiltonian, and now if I solve this equation here, I can actually know what the phi of R1 and R2 is. Okay, so it's the two-particle wave function. The first guess for something like this would be, let's assume it's I can apply separation of variables to this differential equation, and actually I can write phi of R1, R2 as the product of two wave functions. Okay, if I do that, I plug them in here and I assume this solution exists, and this means that particle 1 described by the coordinate R1, it's in a state, in a quantum state called A, and the particle, this particle 2 is in a quantum state called B. Okay, so A and B are different quantum states of the system. This is sort of the idea. That means that the solution 2, it can be written as separation of variables, and in terms of a diagram, it will mean that this is the energy of the states of the two particles, and I have in this energy of the state the two particles is a single state, and I have this particle A, one particle in state A and the other particle in state B, and they both have this energy level together. Okay, so that's the system. So this solution here that I wrote here in 3 is not a good solution if the particles are indistinguishable. What does it mean that the particles are indistinguishable? It means that I cannot differentiate them if I look at them, because why would that happen? Because they are very close. They're inside an atom, for example. They could be the 2 electrons in the 1s level of helium, for example. how can I make a difference where one electron is and where the other is if I only know the probability function for one, okay? And how could I measure this thing? Actually, that is an entangled state in the definition that we're going to see below, you know? But how should that wave function be if the particles are really indistinguishable, okay? It means that phi squared, which is the probability distribution of R1 and R2, if I square that and I change R1 and R2 in that expression, I should get the same probability distribution. If the probability distribution changes when I change R1 and R2, it means that, you know, the particles are distinguishable, not indistinguishable, okay? So essentially what that means is that this solution here is not a good solution for indistinguishable particles, because I know that particle 1 is in state A and particle 2 is in state B. What would be a good solution, considering both of them, if I have them, if I know that this is a solution of that? But you know what is also a solution? Any linear combination of these things, okay? And I use this fact to act, because this is a linear equation. The Hamiltonian here is a linear equation. So if I have this and I add something else, I should get the same solution. What solution could I get? Well, look at what I've done here. I defined phi. This is my trial solution, the better wave function. That is, here it has the same effect as this one, but in the second term here, it has the reverse. Particle 1 is in state B, and particle 2 is in state A. And this is now a wave function that I say it's indistinguishable, and it's equivalent of having particle A and B. And if the particles are indistinguishable of each other, the probability of having one particle in state A should be equal to the probability of finding the particle in state B. So they should be equally probable in this case, okay? And this is what happens here. See, this shows that particle 1 is in state A, and this shows that particle 2 is in state B. And this shows the reverse. I reversed them both. So now, if the particle is indistinguishable, if I change the order of the particle, phi squared should not change. That's exactly what happened here, because this term, when I reverse this term, I get this term, and when I reverse this term, I get this term. So it means that the wave function square will be the same. This in the case of I have a plus sign here, okay? If I have a minus sign, which is the other option, if I reverse the particles, the wave function, the total wave function, when I reverse the particle, they change the sign in a minus sign. There's a minus sign in front, okay? And if I square that, the minus sign is gone. So these two functions that have plus or minus, the B and A interchange, are good wave functions for indistinguishable particles, okay? Actually, the electrons inside the helium atom in the 1s state are indistinguishable particles, because the electrons are exactly the same as the other, are identical particles, and being inside the atom, they make them indistinguishable. It's not that one particle is over there and one over there. The wave function of those are heavily overlapped. So it's really identical and indistinguishable particles, okay? So this is what I've just explained. So if I change R1 and R2, one makes the change. In the case of -1, and the other does not. The square root of 2, 1 over square root of 2, is there simply to maintain normalization. Normalization means if I integrate this wave function over all space square, that should be equal to 1. If that's the case, it means that this is equal to 1 integrated over all space, and this is equal to 1 integrated over all space. So it must have a 1 over square root of 2 to divide the whole thing when I square it and integrate it, okay? So in order to have the phi, this phi here, properly normalized. So this is simply a normalization constant, okay? No big deal about it. So, and here, for example, I forgot to write it up, okay? Yeah, it happens now that if the particles are electrons, they must obey the exclusion principle in addition. If the particles are identical, and these are particles that obey the exclusion principle, it means that A and B cannot be the same. If A and B are the same, it means that these guys are not electrons because they are not fermions. They don't follow the exclusion principle. But look, the wave function that has the minus sign, if I make the B equal to A, gives a wave function that is 0. Perfect. So this thing over here means that the particles if I have a multiple particle wave function, which is representing the wave function of fermions or electrons, which is some form of fermions, and the wave function should be antisymmetrical, meaning it should put a minus sign in front each time you exchange 2 of the particles. And this is exactly what happened here. If I exchange 2 of the particles, I change 1 sign, and if I change 1 sign, perfect. You know, if I happen to have 2 quantum numbers that are the same, and I exchange those particles, that should give 0. Okay, because these are in the same level. So this is, it cannot be. You know, the particles should be completely antisymmetrically under exchange of any 2 particles, and this is true in this case, and it will give a value of 0 for the wave function if 2 of the numbers are the same, okay? Because there will be a change in sign, okay? Oops, yeah. Namely, it means that the particles cannot have the 2 things, and this wave function, the wave function with the minus sign, essentially is a good wave function for identical particles that are fermions, okay? So let's say we measure the state of one of these particles, again, and we find it to be A. What should be the state of the other one? If one is A, well, one chance, you know, if this guy is in A, the other must be on B, because otherwise we'll be sort of not following the exclusion principle, okay? It cannot be that, you know, these are entangled, they are in the same energy level, and they should follow the exclusion principle. That's what it should happen, okay? So essentially what happened is that the wave function that originally was described by this combination, at the end, if I measure one of them, it will collapse to something like this. And this is sort of the theory of how the effect of a measurement has on a state of a system, okay? If you guys like to read, I invite you to read all the literature about the Schrödinger cat, which it says, you know, is the cat, you know, dead or alive, you know, and this is sort of the mystery of quantum mechanics. It's exactly linked to a situation like this, to playing with the macroscopic component of having a system like this, where the wave function collapses to something like this, okay? This only works actually when the dimensions are relatively small and doesn't apply to living things. Okay, so it becomes very complicated at that. But you can look at the paradoxes that somehow quantum mechanics can produce. Yeah. So the measurement process, what actually does, it makes the wave function to collapse. This has been disputed. This interpretation has been disputed. Okay, there are other interpretations that says, you know, the universe has a wave function which is the product of all the wave functions of all the things that, you know, are in any states anywhere. Okay, and when you do a measurement, you actually just choose a path in this wave function of the universe. And essentially what happened if with the other path is still there, it moves in a parallel universe. Okay, so this is not, you're not collapsing, you're actually choosing one of the roads of this multiple component wave function. Okay, so this is the theory of we can call it and it was called like that since the early days of quantum mechanics, of parallel realities. Okay, so if you want to make a science fiction movie, perfect, you know, this is the thing. Actually, the interpretation of one or the other, the collapse of the wave function on the parallel reality, you cannot make a difference on those two models of thinking about quantum mechanics based on a measurement. So for me, that I'm experimentally, it makes really no sense, because the only thing that really matters for me is the actual expected values of the variables that I can measure. I have a theory that can actually predict that independent of the final interpretations of it. That's a good thing. From the point of view of engineering, also, this is what we need to understand. Okay. So this is an entangled state that actually collapsed due to the measurement, and we can have some similar states that looks exactly like this. This is the case in the case of the helium atom. Here I have the helium atom depicted, the potential. I have the 1s state here, and the difference between these guys essentially is you have a wave function that is a 1s wave function. What is different between the 1s wave function to the particle 1 is that it has a spin going up, and this has a spin going down. So the wave function is also a product of a wave function. There's some sort of separation of variables here. There's a wave function that has to do with the spatial component, and a wave function that has to do with the spinor component, with the spin component, and the product of the two in this way, it represents the actual wave function of one particle. Okay, so this thing here is ms equal 1/2, and this is ms equal minus 1/2, and this wave function should be sort of antisymmetric as this is showing here, meaning it should have a minus sign there, in such a way that if for any chances these two things become equal, the wave function should become 0, or, well, the wave function of a pair of electrons should be antisymmetric until the interchange of two coordinates. Okay. So the thing is that we could have this we can think about an experiment in which we send in an electron, we send in another electron, we let them interact in a region where they get entangled. They form an entangled state, and they go out of that entangled state without losing the entanglement. Okay? And because why I want to say something like that, because if I go into this atom over here and I measure that this electron has spin up, I know that the other one has spin down. And one can argue, well, the fact that you measure it, you actually choose this thing to have spin up, and the other guy must have spin down, and the process of measurement actually interfere with the whole thing, and there is some sort of force between the two electrons that actually defines that the spin should be reversed. Okay, but let's say now we manage to actually build a quantum system like this. Then we make the particles interact in this region. We generate an entangled state between these two guys, and we let them separate in an entangled manner. And we measure this guy over here and find out that it's in state A. Well, this guy must be in state B. And when does that happen? When do I know this guy is in state B? Well, it's when I measure here, it should be in state B here, because the measurement is actually what defines the condition here. And Einstein, if you find this spooky, this is exactly the way actually Einstein called it. It's spooky action at a distance or something like that. It says, look, that cannot be right, you know, because there will be an instant communication between this guy and this particle over here. Yeah. How do we solve that? Well, the difference between Einstein interpretation and the actual way today we think about quantum mechanics in this way is that this wave function here is a non-local wave function, meaning it's not a wave function that has to do with only this state. It's something, this system is entangled over kilometers away. Okay, actually they have done this experiment, so this is not what I'm telling you is not science fiction. They have done this experiment and they have measured the, not with electrons, they have to do it with photons because the electron won't travel the far distances without colliding with air and whatnot, but photons can do, okay? And the variable they measure is the polarization of the photons. The photons has particles with spin 1, so they can also be polarized in a certain way. And if you generate an entangled pair of electrons in a position and then they separate, because they don't interact, electrons really much, not like electrons. And well, electrons at a far distance also don't interact. Coulomb's law is good enough over 1/r, finally a meter away, you won't feel the effect of whatever you do to one electron, okay? The effect will be very small. So they have done this experiment and, you know, thousands of kilometers, and they find they are entangled. Okay, so the actual reality works. This is a non-local wave function in two systems. So this entangled thing here, the concept of entangled states also, it has a lot of bearing in quantum computing. Okay, there's this tendency of things to try to understand. I'm not going to explain quantum computing here by no means, but I'm trying to just, you know, put in the seed of things that you have to look for in order to understand this. So we have bits and qubits these bits are in a computer, a classical computer. It's not classical quantum mechanics in all these machines that we're using right now. So and qubits, those are the ones that are in the modern quantum computers. So it's bit associated to a quantum computer versus a bit associated with a computer. If let's say I have in a classical computer, I have 4 bits like this. These 4 bits like this can have 2 to the n different values here. But in each clock step of the computer, they can only have one value, one set of values here at the end, okay? That's not what happens in a quantum computer, okay? Because in a quantum computer, all these guys are entangled, okay? So they are all linked together. So essentially the output here of this, you know, I should have drawn a line here if this is a quantum computer, could be any of these things will be the output. So instead of only having one number here available for each quantum clock not quantum clock, with each step clock in a computer, in a quantum computer, for each step clock here, if here you have one number, here you have 2 to the n, meaning here you have 16 possibilities and here you have only one. And you can imagine that changing the number of qubits change the power of the computation in an incredible way. Now, don't ask me, I'm not an expert on this. I actually, you know, if you're actually interested in reading, please look at this paper over here. So it makes an interesting first look at the fact that you can do, you know, computations in very efficient ways using quantum algorithm. Today, IBM has announced that not today, probably last week. Okay, let's make it better. That they have a core with 57 qubits and it's workable. essentially those are spin qubits. So they should work at very low temperature. It's not something that you could take your computer and take it home, because qubits at low temperature, to make them stable, you need liquid helium. Actually, helium is actually evaporating from Earth, actually. So at the end, we are not going to be able to cool down things to that temperature using a liquid. We should find a good refrigerator for doing that. And essentially, you need a room for the helium to reprocess it, and the quantum computers should all be immersed in liquid helium at probably lower temperatures. It depends on the type of excitations the spins might have inside this computer to make the calculations, and they have entangled them in a certain way. And so they are generating this, they are playing with the idea with having this computer, okay? So this is what I wanted to tell you about the fringes of quantum mechanics, the exotic implications, and this is a sort of things that I cannot go on a lecture, that you will have to read it on yourself. But, you know, down to earth quantum mechanics, I would like you to actually do a homework like this. And I have an example of what you would like to do. I'm asking you to actually find the highest energy state of a particle in a 3D potential well, infinite potential well, meaning a square, not a square, a cube that has infinite potential beyond the size of the cube in any of the directions. So the particles are confined to live freely inside, so they can have a certain kinetic energy inside, but we know that the levels are quantized. So we would like to know what is the minimum kinetic energy, what is the maximum kinetic energy that the minimum state configuration can have, the ground state configuration can have, if I want to put inside that box that has a side of 5 angstrom, and I want to put 20 electrons inside, okay? So this is a good exercise. I actually, I'm hinting here how to do this. This is a one-dimensional thing. In a one-dimensional thing, the energy levels are proportional to n squared. Where's the n? Well, they are proportional to n squared. I didn't write it down here, but it's proportional to n squared. So this is E naught. This is 2. 2 squared is 4 E naught, and this is 9. It's 3 squared, 9 E naught. So this would be the energies. So if this thing here, I said it's 10 angstrom, and then the size of the thing is 10 angstrom, and in this energy level, I can put 2 electrons, one up, and one down. And the next energy level, I can put 1 up and 1 down. And in this guy, I can put only 1. Okay, so the total energy is very simple. The maximum energy or kinetic energy that this electron can have is equal to 9 E naught, and 9 E naught is equal to 6.8 electron volts. Okay, so fairly simple problem. What is the key difference here? You have to remember degeneracy. Okay, you have 20 electrons, and you have to